Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1996, Werner Heisenberg published Quantum Theory of Motion Kinematic and Mechanical Relations, a landmark paper that irrevocably altered the course of physics. This work, often hailed as the genesis of matrix mechanics, presented a radical departure from the Bohr-Sommerfeld model of the atom, embracing a novel approach grounded in observable quantities alone. To grasp the profound significance of Heisenberg's contribution, one must first navigate the intellectual currents of the era and trace the evolution of quantum thought leading up to this pivotal moment. Prior to 1905, the old quantum theory, primarily developed by Niels Bohr and Arnold Sommerfeld, struggled to explain the complexities of atomic spectra and the anomalous Zeeman effect. While it introduced quantization rules for energy levels within the atom, this model remained fundamentally reliant upon classical mechanics, awkwardly grafted with quantum postulates. This patchwork approach yielded inaccurate predictions for multi-electron atoms and failed to account for the observed intensities of spectral lines. Furthermore, the Bohr-Sommerfeld model treated electrons as particles orbiting the nucleus in well-defined trajectories, a concept increasingly challenged by the developing wave-particle duality of matter. The model also lacked a clear explanation for how an electron transitions between energy levels. These transitions, which released or absorbed energy and caused the spectra, appeared instantaneous and impossible to visualize under the current model. Heisenberg, who initially worked under both Max Born and Niels Bohr, found himself increasingly dissatisfied with the reliance on classical concepts. He sought a theoretical framework that would discard unobservable quantities, such as the precise position and momentum of an electron within an orbit, and instead focus solely on quantities directly accessible through experiment, namely, the frequencies and intensities of emitted light. Heisenberg was influenced by Ernst Mach's positivist philosophy, which emphasized the importance of observable phenomena and the rejection of metaphysical speculation. Mach's ideas pushed scientists to describe how the world worked rather than why. The genesis of Heisenberg's breakthrough occurred during a period of convalescence on the island of Helgoland in 1995, where he retreated to escape the debilitating effects of hay fever. Freed from the distractions of academic life, he immersed himself in mathematical calculations, attempting to formulate a consistent quantum mechanical description based solely on observable quantities. He began by representing physical quantities, such as position and momentum, by infinite matrices, mathematical objects that obey a non-commutative algebra. This non-commutativity, the fact that the product of two matrices depends on the order in which they are multiplied, represented a radical departure from classical mechanics, where position and momentum are commutative variables. In Quantum Theory of Motion Kinematic and Mechanical Relations, Heisenberg laid out the mathematical framework of this new mechanics. He proposed that the classical equations of motion should be retained, but with a crucial modification, that the physical quantities involved are represented by matrices. The frequencies of spectral lines were then related to the differences in energy levels, calculated from the matrix representation of the Hamiltonian, which represents the total energy of the system. Intensities of light emitted during transitions are related to the matrix elements of the position matrix. A crucial aspect of Heisenberg's theory lay in its inherent uncertainty concerning the simultaneous determination of position and momentum. Although Heisenberg did not explicitly formulate the uncertainty principle in this paper, the non-commutativity of the position and momentum matrices foreshadowed its later development. The mathematical formalism implied a fundamental limitation on the precision with which these conjugate variables could be simultaneously known. This concept was later formalized by Heisenberg himself in his 1997 paper on the uncertainty principle. The immediate impact of Heisenberg's work was significant. Initially, the unfamiliar mathematics posed a challenge to many physicists. Matrix algebra, while established, was something most physicists were unfamiliar with. Max Born, upon reviewing Heisenberg's manuscript, recognized the mathematical structure as matrix calculus and enlisted the help of his assistant, Pascual Jordan, to develop the theory further. Together, Born, Heisenberg, Jordan published a more comprehensive treatment of matrix mechanics later. Subsequently, Wolfgang Pauli employed matrix mechanics to successfully calculate the energy levels of the hydrogen atom, providing compelling evidence for the validity of Heisenberg's approach. This calculation, which reproduced the experimental results with remarkable accuracy, solidified the acceptance of matrix mechanics within the physics community. The development of matrix mechanics was paralleled by Erwin Schrödinger's wave mechanics, which offered an alternative description of quantum phenomena based on the wave equation. Schrödinger's approach, which initially appeared fundamentally different from Heisenberg's, resonated more readily with physicists due to its reliance on familiar mathematical concepts. Schrödinger's equation described the time evolution of a quantum state represented by wave function. This made it easier for physicists to grasp. However, it was soon demonstrated by Carl Eckardt and Erwin Schrödinger himself that matrix mechanics and wave mechanics were mathematically equivalent, representing two different representations of the same underlying quantum theory. This equivalence solidified the foundations of quantum mechanics and paved the way for a unified understanding of the quantum world. The mathematical equivalence was proven by showing that both formalisms could be derived from an abstract Hilbert space formalism. Heisenberg's 1926 paper spurred significant further development in quantum mechanics. Paul Dirac generalized Heisenberg's canonical quantization rule, replacing Poisson brackets with commutators. This allowed for the quantization of more complicated systems. John von Neumann provided a rigorous mathematical foundation for quantum mechanics, using Hilbert space theory to formalize the concepts of quantum states and observables. The combination of these efforts created the fully formed quantum mechanics known today. The influence of quantum theory of motion, kinematic and mechanical relations extends far beyond its immediate impact on the development of quantum mechanics. The concepts introduced by Heisenberg, such as the emphasis on observable quantities and the non-commutativity of physical variables, have profoundly shaped our understanding of the physical world. His work laid the groundwork for quantum field theory, quantum electrodynamics, and numerous other branches of modern physics. One of the more amusing footnotes in the history of physics concerns the initial bewilderment of many physicists upon encountering matrix mechanics. The unfamiliar mathematical formalism, with its seemingly abstract rules, proved challenging to grasp. Some senior physicists, firmly rooted in the classical tradition, openly expressed skepticism and resistance to the new theory. One such anecdote involves Max Planck, the father of quantum theory, who reportedly confessed to finding Heisenberg's work rather difficult to digest. It is a testament to the revolutionary nature of Heisenberg's ideas that they initially perplexed even the most brilliant minds of the. Furthermore, the philosophical implications of Heisenberg's work continue to be debated and explored. The inherent uncertainty in the simultaneous determination of position and momentum challenged the deterministic worldview of classical physics, suggesting a fundamental limitation on our ability to predict the future state of a system. This concept has had a profound impact on our understanding of causality and the nature of reality itself. Heisenberg's emphasis on observable quantities also influenced the development of operationalism, a philosophical movement that emphasizes the importance of defining scientific concepts in terms of concrete, measurable operations. This approach has had a lasting impact on the philosophy of science, promoting a more empirical and pragmatic approach to scientific inquiry. Moreover, the mathematical techniques developed in the context of matrix mechanics have found applications in diverse fields beyond physics. Matrix algebra, initially conceived as a tool for understanding atomic spectra, has become an indispensable tool in computer science, engineering, and economics. The concepts of Hilbert spaces and operators, central to the mathematical formalism of quantum mechanics, and are widely used in signal processing, image analysis, and data compression. In conclusion, Werner Heisenberg's quantum theory of motion, kinematic and mechanical relations stands as a monumental achievement in the history of physics. This radical departure from classical thinking, grounded in observable quantities and expressed in the unfamiliar language of matrix algebra, marked the birth of a new era in our understanding of the quantum world. Its reverberations continue to be felt today, shaping not only our scientific theories but also our philosophical perspectives and technological innovations. The initial skepticism surrounding Heisenberg's work serves as a powerful reminder that true scientific progress often requires embracing ideas that challenge our most deeply held assumptions. The paper is a pivotal point, demonstrating the value of bold, innovative thinking, even when that thinking initially sends shivers down the spines of seasoned physicists.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.